Hi, my name is David Lamayan. I am based out of Kenya. I am supporting the team at Qubit Hub to really catalyze AI adoption across the continent. I wear a couple of different hats, but today I'm excited to be moderating, or rather, just introducing Dan and the work that we're doing with the Compute for Africa program. So, just to set the stage, compute is something that's very important to getting things done in today's world. And there are a couple of ways that you get access to compute, right? So you pay AWS a couple of billions of dollars if you leave it running for too long, or you pay, your Googles or Microsoft, a few $1,000s to get servers hosted in different parts of the world, right? I remember when I started out, I don't know how many years ago, over 10 years ago, to be able to get a server to be able to host, a small website project that I was doing, I had to sell a cow. I had to sell two cows. Now that was very expensive. Um, but then today we have the power of what we're calling distributed networks, and what the opportunities are there, right? It's not exactly for the hosting of of my project, but it can answer a lot more other questions. So with us today is Dan, Dr. Dan. He's a PhD scientist. He's CEO at Distributed, but he also did his PhD in physics. In fact, it was in applied electrodynamics, which pretty much makes him a rocket scientist. And a lot of the, but he'll talk about what he then came up with when he was doing his PhD, when he was trying to crunch lots of numbers, and then discovered, hey, we have a bunch of computers here. It's taking me hours or days to run these simulations. Can I just run it on multiple computers at the same time? And that's where I think the genesis of distributive came about. So we're excited to have him. We're going to go through, what is distributive? What is this new technology? What does it mean for us? And then we'll talk about the opportunities that we have to partner with you and your teams to make it available, and hopefully reduce, the cost that you have for compute. Hopefully you don't have to sell a cow. But yeah, over to you, Dan.
Hey, David, thank you very much, and welcome everyone. I've been looking forward to this presentation because I get to inject a little bit of personal passion around scientific computing, and everyone here is probably interested in their own form of research, and I'm suspecting it's going to be largely around AI, which is good. AI drinks compute in order to make things happen, and so maybe before getting into, like, I was trying to debate how do we do this? Do we start with the vision or start with the technology, right? Because engineer types will want to see the code and the hands-on right away, and then the big thinkers will want to see the why first. So I'm probably I'm gonna do a flip-flop. I'm gonna start right away showing a little demo that won't reveal too much, but it'll get everyone engaged because it's interactive. And then I'm gonna go into the why, and then I'm gonna come back on the technology more at depth. And then I'll say right now, the bottom line up front, or the goal, is to solicit from the group here folks who have use cases that can run on this. Because it's not just about reducing the cost of compute, but it's about redirecting the flow of money that right now is going to foreign hyperscalers for the most part, and redirecting that into local, sustainable, equitable compute economies. Okay, why is it that foreign hyperscalers are making all the money on the rising tide of AI? All that value should be captured as much as possible locally within local geographies. Okay, so we'll put that's just a sneak peek of what comes next, but let's just get right in with an interactive demo. What I'm going to do here is I'm going to run a physics job, my own research, across all of your devices live on the call. And then I'll explain how that's possible, and then what that means for unlocking compute on a continental scale. So conveniently, this application, this physics application, takes the form of a website. I just want to do a check. David, can you see my screen? Is this transmitting properly?
Yes, we can see your screen.
Okay, great. So I don't want to dive into the specifics of this use case, other than it's pretty cool and it's all to do with electromagnetic propulsion and space elevators and that kind of stuff. But what's really important is I wrote some code and I want to compute it, and it takes a long time to compute. But if I can spread out the problem in little pieces across more computers, more devices, I can get my answers faster. That's basically what the cloud is when you think about it. It's a building full of computers, servers, or what have you, that you can spread workload out and get your results back. But the thing is, it's quite expensive and it's most likely in a different country. What if you could take hundreds or thousands of computers that are all around us, bought and paid for and already on, and turn them into your own cloud? Maybe even make money by having it run compute for other industries or people or consumers or local businesses or whatnot, instead of having that compute be performed offshore. So anyway, this use case here, I don't want to get into the specifics, but it's a lot of computational modeling, not unlike the modeling that you would do in data science. And by that, I mean I have expensive functions and I need to traverse a landscape, a hyperdimensional landscape of parameters and compute stuff. And I'm looking for maximum thrust to weight ratios and things like that, kind of like hyperparameter tuning, where you're looking for the best performing pairs. What I'm going to do here is I'm going to punch in a couple of numbers, and these are all going to generate plots. And because of how many we are this morning / this evening, I'm going to make this take a little bit longer and make it more fine-grained. This will provide about 200 slices of computations. So what I'm going to do here is I'm going to hit compute, and now this job from my computer just went up into the ether, and I need everyone on the call here to open on a device dcp.live. And I can tell some people have already done it, who already knew how to do that. So dcp.live, and what you should see is something that looks like this. And if you hit start, you're going to pull a task called emcoil. And as everyone does that, this progress bar is going to move faster and faster and faster, because there are more and more devices all around the world. Like, I'm in Canada right now, and many folks here are obviously in Africa, but I know there's some people who are also in Canada and maybe even from the States, because we broadcast on LinkedIn and to get maximum attendance. But the point is, any computer, anywhere, running any architecture and any operating system, as long as it's fit for purpose, and by that I mean it has enough RAM and it's suitable for the task at hand, it will compute and it will execute these little slices and send back results back to me. And so I want everyone to think about what just happened. We created an instantaneous cloud with a single click, using all of our devices and the current audience to do some sophisticated physics computations. And I'll come back to that. And there's a whole bunch of security considerations that go into this, but there's also some economic considerations. You've probably noticed, for those who did run workers, you've accumulated something called compute credits, and those have a cash value. And so imagine now an economy where people can buy and sell compute and trade compute, okay, from local geographies, instead of, so that keeps wealth. And the true money-making opportunity from AI right now, I believe, and I'm biased, is being scooped up by the hyperscalers. That's where all AI, where all big stuff is being run. And so as a Canadian, I feel that the rising tide of AI in Canada is penultimately benefiting hyperscalers. And that's not what nations want in terms of sovereignty and self-determination. Furthermore, the hyperscalers are freaking expensive. So I got my results back, pretty plots, and I can tell a story about the physics here that I'm quite proud of. There's negative drag in certain frequency velocity regimes and so on and so forth. But I'll leave that to another scientific talk. The point is, there are computers and devices all around us, and tapping into them can allow us to do more scientific advancement. AI is one form of compute, but data processing, image processing, scientific computing, numerical modeling, plasma containment field, simulation, all these things are facilitated by compute. Okay, so that's the what. Now everyone hopefully is engaged and like, whoa, how did that work? I want to get to the big picture, and then we'll come back to sort of the opportunities at hand and what we're looking for. So I'm calling this talk Beyond the Cloud, and it's a real pleasure to be working with David and Kala and Qubit because we are our goal is to unlock almost free, like so cheap that it's almost free compute by recycling computing infrastructure from everywhere. And when you do that, if you pool this compute, whether it's in publicly available or privately available networks, you can create compute economies that benefit local areas. And here's why. So this is the ultimate big picture. Here is GDP as a function of compute capacity. If you have more compute capacity in your country, you'll be able to do more advanced research. You'll be able to do more bioinformatics, more AI, more aircraft, airframe simulation, more everything. And that's the true catalyst for innovation today. And I say this as a computational physicist. I'm not running around testing every shape of coil for my hyperloops. I'm computing the best simulations. When people are doing cancer research for potential therapeutic enzymes or molecules, they're not testing, with test tubes every possible combination of chemical. They're simulating the best possible candidates and they're synthesizing the most promising ones. So compute is an enabler for those who can afford it, and it's a showstopper for those who cannot. Canada is on this plot, and we're pretty much last in the G8, or we are last. We're dead last in the G8. On the map, we also see South Africa and East Africa. I don't even know if there's enough data to be able to put them on the map. And so compute is critical. I hope that this drives that point home. So if you want to develop the economy and the innovation and discovery capacity of a nation, you need compute capacity. Then how do you source it? Well, the obvious one is build a bunch of expensive data centers. And that's what everyone is trying to do, and they're fighting over each other to get those NVIDIA GPU chips. The other alternative is rent cloud. And right now, those are the big four hyperscalers, and that comes at an extreme cost. So the trade-off here is buy and build. You have a national at-home sovereign compute capability, which is critical for self-determination, to not be reliant on foreign capacity. But building data centers takes hundreds of millions of dollars, depending on size and scale, but also several years. And if it has to go through a government procurement program, at least in Canada, now we're talking a decade. The trade-off, if you want compute almost overnight, is you rent it, from someone else. But those folks are trying to, they're not charging you for just compute. They're charging you for their operations and the overhead, obviously the electricity, but most importantly, amortization of the hardware. So they want everyone to pay for their acquisition costs of hardware, and then they're sitting on the asset. The third option is one that people are aware of, at least in an almost acute way. If people have heard of SETI at home, it's been around since probably the 80s, where volunteer networks provide computers to do scientific volunteerism, if you will. It's never really gone beyond that. There have been attempts in recent years to use cryptocurrency and all this other stuff in blockchain to create compute shared economies, but it didn't land right, or I haven't really seen a credible cryptocurrency-backed distributed compute platform because for credibility reasons. And I say this as a professor. I don't see hospitals or manufacturers or governments paying Bitcoin, that's volatile to compute, biomedical research, applications. So It has its use cases and its space, but it's not, I think, viable for real pure and applied industry use cases. There's also a security issue. If I said, hey, run random code on your computer that I gave you, you'd rightfully say no. And yet, there is a technology that exists that everyone takes for granted. In fact, we're using it right now on Zoom. It's called the internet. And it's been perfected over multiple decades with tens of billions of dollars to be able to execute securely arbitrary code from arbitrary locations and arbitrary providers on arbitrary computers and devices, from watches to fridges, running arbitrary operating systems. Well, that's one excellent security concept. And so imagine building a compute platform. And so that's what we're going to present a little bit later in the technology, but I want to bring this back really quickly to the economics. This is a C6G 2x large. If some of you don't know what that is, I don't blame you, because it's one of 700 instance types that you can rent from AWS. And me as a physicist who only cares about my physics code, I don't even care. I don't want to know what this is. I just want my results so that I can publish and do my discoveries and move on. But I chose this one specifically because if you see the definitions down here, the C6G 2x large has 8 vCPUs and 16 gigs of RAM, and it doesn't even have a GPU. Okay, this is just a pure CPU instance. My laptop that I'm on right now, for example, has 8 vCPUs and 16 gigs of RAM and the M2 GPU chip, which is pretty performant. So my laptop right now has way more power than this instance. And yet, renting this instance for 12 months under the compute savings plan costs almost 1,200 US a year. And that's fixed in for 3 years ahead of time. So some might have heard of the iPhone 14 index. They're basically showing differences in purchasing power parity across the world. And what they're showing here is the percentage of the median salary required to afford an iPhone 14 all around the world. To be cheeky here, I redubbed this the C6G 2X large index because it's about an iPhone, is actually a little bit lower than $1,000. So this is actually more expensive than an iPhone. But this sort of puts things in perspective. In Kenya, if we believe this, 61% of the median salary would have to go into renting 8 vCPUs and 16 gigs of RAM for a year, right? Compared to less than 2% in the US. So who has access to compute from a monetary point of view here? This asymmetry in costs is creating an asymmetry in access. And compute is the limiting fact. Compute and data are the infrastructure are limiting factors for the pace of AI development. And when we read some of the comments and going down the Reddit posts, people around the world are agreeing with these stats. And the cloud compute is a globalized price. It's not a different price depending on where you are. It's the same everywhere. The high margin areas subsidize the low margin areas, because if there were pricing differences, people in New York City would just move their workloads to South Africa, for example. So unfortunately, compute is a globalized price through the hyperscalers, which hurts because Africa, nor Canada, nor anyone for this matter. I mean, this is obviously talking about Africa, but this is everyone. Nobody wants to be left behind in the global AI race, and want their voices heard, and want to fine tune and adapt and play a role in discovery and advancement. Africa specifically has interest in agriculture and healthcare and financial inclusion, for examples, but beyond. And just like Canada, there's limited infrastructure and data, and talent retention is an issue because everyone's following the money and the compute, for that matter. Okay, so what's going on about this? Qubit Hub, Distributive, and a whole number of other partners are involved currently in a 5-pillar initiative to to do something about it. David and I are digging in this specific pillar called Compute for Africa, which is really focused on unlocking abundant compute from existing infrastructure that already exists, and not just making it cheap, but like I said, creating an economy out of it and making that compute accessible. So the example that I did so proudly of my own physics research that took long times when I was doing it on my laptop, but was sped up when I could tap into multiple idle computers that were sitting around doing nothing at my university. That's the idea here. So if you want to do big things, you need big infrastructure. And if any of you, and this is where, this is not just marketing, this is actual API. If anyone on this call has a use case where in their source code somewhere, they're invoking some sort of loop like this, where you're saying, okay, declaring a results array, and then I have a whole array of inputs, and I have some computationally expensive function that I want to run across all of those inputs, and then append those to a results array. If you do these in a for loop, this one obviously is doing them one at a time, but with threading, obviously you distribute them across the cores on a laptop. But if you have millions of inputs and an expensive function, let's say it takes 10 seconds or 30 seconds or a minute if you're doing some, some sort of random forest training application with high dimensionality and lots of data and iterations, etc., that's going to take millions of seconds. But if you have thousands, or even, let's be bold here, millions of computers, it makes intractable problems, intractable due to time, but also intractable due to cost. It makes them all of a sudden tractable. So reformatting, if you imagine the part in your code, let's say it's hyperparameter tuning or batch inferencing or image processing with millions of images from drones or satellites or whatever, it can be refactored as what you see on the right. And that's the Compute API by the platform that we're slowly introducing as part of the Compute for Africa initiative that will take those inputs, and that function will create a job handle and then call execute on it. And then all those pieces of job will execute, distribute automatically, and return a results array exactly as it would be on the left, but just in parallel and simultaneously. There's probably some excellent questions in the chat. I'm almost through the high-level stuff. I'm going to pause. I'm going to take questions, and then we will go into some applied technical stuff. So in summary, there's an API where people can express workload quasi-trivially as long as it's distributable. Okay, so inherently non-distributable workloads that are serial are not a fit for this platform. And there's lots of stuff that this platform will not do. It's key that the algorithms, and I have a list of them at the end, have to be data parallel from the get-go. Otherwise, it's automatically not a fit. The scheduler, bank, and portal, and the bank is an interesting one. That's where money transacts between both sides of the equation. And then on the other side, you have software agents, workers, that we call them, that can be deployed as Windows screensavers. So imagine a hospital full of dozens or hundreds of computers, or a university campus, or a college campus, or even a high school deploying screensavers that whenever the computers are idle, those computers automatically, when the screensaver comes on, join a compute cluster that is then available to do AI or research computing or whatever else, right? And then if someone moves the mouse, the screensaver stops, it stops doing compute and it goes back to being a normal computer, right? So imagine deploying screensavers on thousands of computers so that they're only in use when they're idle, reclaiming compute power. There are browser workers where only a couple of lines of code, actually the browser worker, the demo I did at the start of this, if anyone's wondering how that worked, about 5 or 6 lines of code behind the scenes allow folks to tap into the computing power of machines on that website. And so as a really extreme but totally feasible example, if youtube.com were to put our 6-line browser worker code in their index.html, we would gain 160 million compute nodes like that. And what's cool in that use case is, I'm now on a bit of a tangent here, but it's an interesting use case, and I want to make everyone dream here of some really cool stuff. When you upload a video to YouTube, you know how it says processing? Well, what happened is that content went to GCP servers, and it's transcoding, and then it's being served in a variety of different codecs, et cetera, and resolutions to consumers of that content on the YouTube network. Well, while those GCP servers are doing that transcoding, computationally expensive transcoding, those servers are not available to industry, Goldman Sachs, or whatever companies. And so it's lost revenue in the form of GCP servers that are transcoding petabytes worth of new content being produced every week on YouTube. Meanwhile, YouTube is forcing people to either pay or watch ads. Imagine if there was a third option where when you're watching YouTube content, in the background, your computer would be doing compute for transcoding the new content that's being uploaded, which would free up GCP server capacity, which will allow them to go make revenue elsewhere. And that extra revenue could offset the ad revenue for the people who don't want to look at ads and don't want to pay for YouTube Premium. So it's kind of like hey, welcome to YouTube. Do you want to stare at ads or do some compute in the background? Remember my choice. And it would be the same thing for any online community where you have this sort of self-propulsion of content that needs to be processed, like Instagram or what have you. So that's the browser worker application, which is totally unique to this platform, and there's nothing else that exists to do that at scale. We have Linux workers for your classic enterprise servers. And of course, we have Docker workers where a single line of code can be used to generate a worker and does work. And you can also generate YAML files for existing kube fleets to basically push that image out and create giant worker clusters. Anyway, all to say is there's all kinds of options to leverage computing power from arbitrary types of devices. And believe me, we've done physics on a fridge just to prove a point. And this is how we can tap into compute across Africa and Canada and Latin America and all over the place to create local compute economies. Okay, let's get into the tangible. So if that idea sounds attractive and exciting for all the reasons, economics, money making, reducing the cost of compute, all that good stuff. Okay, well, let's talk about what use cases. And remember, like the goal of this webinar is to solicit interest from everyone to see, okay, who has use cases that we can run as part of this this pilot right now? And the more, the better. And tell all your friends and send them the recording after this call. So we've already completed one of 5 use cases that we're intending to run to prove the point that it's at least 10 times cheaper than commercial cloud. So welcome to Africa Nazarene University's distributive compute cluster. They have about, I forget, 10 or 12 computers in this lab. They did a small test cluster where they deployed the screensaver. And right now the screensaver, you can see it's showing our logo, but they're as of 2 a.m. this morning, it's showing their logo as it should be, but it's basically capturing all of that computing power from that classroom. And it was used to perform a hyperparameter grid search, specifically random forest training and evaluation for a natural language processing use case that's basically doing sentiment analysis on tweets. Again, just like my physics example, the use case isn't, the specifics of it are moot. The point is, if it's distributable as a hyperparameter grid search, then you can run it on this type of platform. Just to go a little bit behind the scenes, some of you will recognize, random forest classification type problems. And you can see that it would take a long time to compute through the grid of parameters here. In fact, there are nearly 14,000 parameters that were searched in this search. I did it on my laptop just to see how long it would take as a researcher who couldn't bother to use AWS or get into DevOps, which I'm not a DevOps engineer. I'm a PhD physics. I don't want to do a PhD in DevOps. I'll leave that to someone else, which means now I have to pay a whole team to do DevOps for me, which is also annoying. So I ran on my laptop and it took almost 4 days. And my laptop was slow and sluggish, and it was painful. I was trying to do Zoom calls and stuff, and things were choppy, and it was annoying. And not to mention, the most valuable thing isn't really the AWS bill, it's my time. I had to wait 3.5 days before getting my results to see if they were good or if I have to change the code and repeat again. And so um, time, I think, of a developer is equally, if not more valuable than the compute they're consuming. And this is why the cloud is making a lot of money. It's because there's an incentive to spend as much as possible, as fast as possible, to minimize how much time you're wasting. But then you end up spending more faster on the cloud. So it's devious, but it's just pure economics. So anyway, take this problem and we ran it on AWS, and it completed, I forget how many hours here, it took over a day and a half, and it was $44 US. And we ran it on this platform, it ran for under $4. And so there you go, smack in the middle of the target, or below or better than the 10x reduced cost. Okay, so that's one use case. And there are a couple of more that are ready to roll. We're doing one at JK Watt, Jomo Kenyatta University of Agriculture and Technology, where we're processing drone imagery to look at NDVI, which is natural differential vegetation indexes from imagery captured by drones, which is crucial for deforestation and smart agriculture, and even weather modeling and soil aridity and all kinds of important stuff that affect crop planification and agriculture and what have you. Beyond that, we have an ML batch inferencing computer vision use case that is also ready and undergoing testing. So we're well on our way to having 5 use cases where we're basically proving out local sovereign compute 10x cheaper than cloud to enable compute-driven innovation. But that's just 5 use cases. We want hundreds of thousands of use cases. We want to take this continent-wide. So the call to action here is, please fill out the survey that will be provided to you. We're looking for distributable use cases to get on this platform and prove it out, and do a gigantic pilot, continent-wide pilot after this one. In summary, this is the current problem, is that as researchers and AI rises, compute consumption rises, and it really benefits, especially for Canada and Africa, and basically everywhere except the United States. It benefits AWS, Azure, and GCP. They're the ones raking in the cash. The model we're proposing, the vision we're proposing, is to cut up the pie, have proportional revenue models for everyone. If you're providing compute, if you're providing algorithms, if you're providing data, if you're providing infrastructure, if you're providing networking, if you're providing orchestration, or if you're evangelizing, there's something in this for everyone. Let's cut up, let's divert the large hyperscaler cloud spend, cut up the pie and share it. And that's how you create a true economy, right? With proportional and shared incentives. And so as the rise of AI occurs, and not just in Africa, Canada and Latin America and all over the world, it makes sense, and it's totally strategic for a country to posture and build capacity, sovereign capacity at home, so that it can hold on to more of the value that it's expending to create that AI value. This is a note on carbon footprint, and we can keep this for another chat. So that's the end. The next couple of slides in the annex go through sort of a menu of use cases that are fit for distributed computing. I'll run through those after, but I think now is a good time to pause and say, let's build tomorrow's compute economy together. We need your use cases. We want you to sign up. We want to hear from you, and we're going to reach back out. But for now, I'm going to pause. I'd love to hear questions from anyone. Feedback, comments, anything.
Thank you, Dan. I think we have one question in the Q&A section. Philip, I don't know if you want to come. I don't know if Martin, are we able to give Philip the microphone? Or if Philip is able to come onto the microphone and just ask his question.
Okay, thanks. I won't be too long. I think the question on the chat was fairly self-explanatory. Obviously, you're leveraging idle compute, but then what happens when that compute, because obviously it's not static. There will be days or times when either because of a blackout or a power outage or just people shutting down their computers at the end of the day, perhaps it's company policy, so it will be all over the place in terms of what's available at any one given time. So how do you even that out just to ensure that, there's value for all those who may sign up or sign into this service?
There's two options, or there's two explanations. The demonstration that I did at the start of this call, the workload was split into little pieces and it went to everyone's computers on this call. I am almost certain that someone stopped, paused, or closed that tab mid-compute, either because they were worried about it or they're like, oh, wait, what's going on here? Or did it just for fun. And what happened automatically behind the scenes is that each slice has a heartbeat signal, and if that heartbeat signal goes quiet, the scheduler retasks the workload slice to another available node. So that's one response, is the self-healing nature and the respawning of workload slices dynamically without needing any intervention. The other response is that the screensavers capture idle compute, right? And they're designed to do that. But if you were to run, for example, the Docker worker or the Linux worker on dedicated infrastructure, you would have a dedicated compute cluster. So this platform, DCP, can be used either as dedicated or cycle scavenging, or a hybrid of the two, depending on how the IT folks configure it at their end, if that makes sense.
Sure, thanks. It does.
Great, thank you, Philip. I can see we have a question from Job. Are you able to come off of mic, or maybe Martin, you can see John Minor, sorry, John Minor. Yes, thank you. John, I think you have the microphone now, if you're able to. If you're not, I can read it out as well.
Okay, good day to you. Am I audible?
Yes, we can hear you, John.
Oh, yes, yes. There were some slides I noticed about, I think it was carbon emissions. I was actually able to, it's a field that you actually focus on regarding having a sustainable framework, like issue of climate action, which actually is brought about by high computing. So the question was, like when you actually mentioned something about idle computing, the issue is like, how do you create like a mechanism whereby when there's actually high internet demand, other companies use like green energy to power their cloud servers, but regarding computing, is it possible for you to have high computing power, but at one point you're actually keen on like having a sense of sustainability due to like energy demand? So that was actually my question. It's mainly about power and energy, not entirely about cloud services.
Excellent question, John. So yes, the word sustainability gets used a little bit too much without being defined nowadays, right? And so there's environmental sustainability, and there's economic sustainability, and others. So economic sustainability was the one I was keying in the most in this presentation, because it is not sustainable to have foreign hyperscalers raking in all the cash expended to do all this AI. But from an environment perspective, that's another interesting topic of discussion. So it's very nuanced, and now we're going to do one of these, okay? What is more energy efficient? Renting computing power from a bleeding edge, high efficiency, centralized data center with centralized environmental controls, or using a bunch of 5-year-old desktops, that have been around for a while and are starting to approach end of life, or at least midlife? The answer is joule for joule or watt for watt. It's obviously more efficient to compute using high efficiency centralized data centers. But that's sweeping a lot of like the whole picture under the rug. How much money does it cost, and how much how much energy goes into producing new silicon chips, and how much farmland gets taken up, and how much water gets used, and how much, like, the total cost of building a new data center. If you look at the total energy that goes into that, it's non-trivial. Like very much non-trivial. And the other angle is these computers that are already bought and paid for, they're already sunk costs from a materials perspective. And so there's zero incremental hardware production, manufacturing costs associated with infrastructure that's already there. And then presumably those computers, most of them, or at least if we're talking about data centers, like imagine a bank or whatnot, all those, or in a Safaricom, let's say, all their enterprise servers are already on and powered up and probably use at about between 20 and 40% capacity on a regular basis because they need peak capacity on reserve. So you have a bunch of machines that are already bought and paid for, already on and powered. And so now see, this is what I mean by it's all nuance. Now what's more efficient? The incremental cost of electricity on already bought and paid for infrastructure that's already on and powered versus a new build out, right? With everything included. The answer, and I'm not trying to bias this toward just towards this psycho-scavenging technology. I think the answer is going to be in between. Any capacity building strategy for any nation should maximize all three strategies: a mixture of buy and build for the really heavy stuff, rent for the really quick fix and short burst stuff, and then recycle existing for the lower tier compute needs. So for example, if you need H100s or H200s or whatever with more than 100 gigs of RAM or whatnot, this platform is not made for that. However, running small workloads on that high-end infrastructure is kind of like taking a Ferrari to the grocery store to pick up milk. It's overkill and it's wasteful. And so the most intelligent thing to do is take the lower medium tier distributable workloads and put them on these types of low medium tier distributed systems and reserve the HPC infrastructure for big HPC workloads. So that answer is sort of nuanced, but hopefully makes sense.
Yeah. Great. Thank you, John, for that question. And I know quite a few UN research reports that say, how these new data centers are really siphoning up all the water and taking up quite a bit of the precious minerals that we have in our continent. Okay, cool. So we're going to try and power through these. People have now come and asked a lot of questions. So Dr. Dan, we power through these questions as best as we can, and then we're going to, of course, have the email address up for everyone to be able to also ask questions later. So I guess then we have Felix Ochoga, Felix from Hikope, who had one question. Martin, if you can give, and then Akola, one question, and Olumoko once we are there, and Alan Paul, of course, just not a question, but feedback. Thank you for that.
Okay, can you hear me?
Yes. Felix.
So my question is on the practicality of and the use case for fintech platforms. So we're looking at, yes, I'm a startup or we're a startup and we're in payments and all that. And there is a lot of huge data that you have to kind of use and you have to do cloud computing. And at the same time, security, how secure are you is a huge concern, even from the development side. So are there some use cases? And if in case there are any use cases, how then do you tell a founder who is in payments is looking to, compete with the bigger juggernauts like, Flutter, Paystack, M-Pesa, and so forth, but still offering using less money, but still offering quality services at the same time? So that's a huge concern. So I'm wondering, is there a use case, and how then are you able to factor that in the sense that I can literally trust and say, okay, I'm going to use distributed computing, but then I can use it not just for today, but I can do huge volumes. When I start processing payments that are in billions of dollars, as an example, that I won't have the system crashing. Are there use cases, and how can you work on that?
Felix, it's good to see you. I recognize you. We had an email exchange last week, and I'm looking forward to connecting with you next week.
Yes.
Very good. So I know where you're going with that, and I have just the answer you want to hear. So this is all to do with the financial settlement layer. So as mentioned, and we haven't really done the deeper demo, and maybe we'll do that later if there's time. If not, I'm really happy to do a part 2 if we run out of time. But basically, what I'm going to back up because this is an interesting part of the narrative. Why are the hyperscalers so dominant? Because at the end of the day, fundamentally, they are buildings full of servers. There is nothing unique about a building full of servers. What they have done extremely well is instrument those servers with billing and metering capabilities. And so everyone has become dependent on that billing and metering layer in order to operationalize their business models. So every SaaS company out there, how do they go about charging their customers? It's tough. But if you put it on AWS and then you just do a markup, it's all automatic. And so it's the business logic layer that really differentiates the hyperscalers, in my opinion. They're running software, they have a bunch of green blinking lights like every other infrastructure provider or just self-consumer or whatever, but it's the business logic that makes it important. So DCP has a couple of things that's unique to it. So I mentioned earlier that it's built on web technologies, which gives it the infinite interoperability, like write code once, run everywhere on anything, regardless of operating system, chip, and everything else. And that's great interoperability. The security angle is critical too. The ability to execute arbitrary code on arbitrary machines with the same security assurances as Google provides or Opera or whatever when you're surfing the web, executing untrusted code from whatever data center or web server it's fetching data from. That's a really narrow and excellent security profile for a compute platform. But the third and key critical part is the business logic. So the ability to dynamically meter how much compute is being used by which jobs on which computers, and being able to mediate or meter and then move these compute credits around proportional to usage. That's the key part that allows a compute economy or a transaction for that matter to occur, is the ability to measure. Here's the cool part, and this is what I wanted to meet with you and talk about next week. I don't care about what that settlement layer is. The important thing is the measurement and the metering. And you can measure it in credits, you can measure it in cows, to use David's example, right? You could literally measure compute in cows if you want, as long as the cow has a value and you ascribe a value to CPU, GPU, bytes in, bytes out, whatever. And so once it's measured, regardless of what unit you choose, as long as you have a measurement, a unit of account, we call it that, then you can use whatever you want to settle the financial aspect of it. Distributive is never going to get into the game of going around to every bank around the world and setting up trusted relationships to facilitate international transfers. Not going to happen. It's way too big. There are companies who have succeeded in doing that. PayPal or Bitcoin is it's the cryptocurrency fintech, or there's a number of companies that have sort of solved that user-to-user merchant transaction, and Distributive is happy to partner with all of them, yours included. In fact, we want that. We want that, and we invite that, because the more options there are, especially if they're local options, people will be more happy to transact with, again, local technologies that come together. So this goes back to the proportional business models that I was mentioning earlier. We want everyone, the compute providers, the application providers, the data providers, the network providers, the orchestration providers, the fintech layer payment transaction clearinghouse providers. Everyone should be taking a cut in a consortium-based approach to creating a compute economy. And that's why when you reached out to me, I was more than happy to say, yeah, let's talk about this. Does that make sense? So my answer there is we're going to have total open doors to any settlement layer that people want to put in this, so people can choose.
Okay, I don't know if I can still be heard, but yes, it answers a bit of it. I think the one thing that is a huge concern, because I think when we talk up when we compare all the different cloud providers and so forth, and the one thing that you're looking at is, can I have a system that is almost flawless when you're transacting? So I think that bit is one thing we're going to talk about. Now, I think the other thing I wanted to ask is, so I'm kind of involved in trying to set up a digital lab in Kenya across different regions, and you're trying to do them in out of Nairobi. So we have like computers like 30 to 60. We can provide normal lessons, Google-based lessons for young people, coding and programming skills, and so I'm also thinking that, yes, as I'm talking about this, probably that's also another line where you may want to shed light upon, so that we're looking at the existing, should I say them, cybers that are almost going extinct in Nairobi. But of course, when you go to out of town, the bits still there's still many. How then could they also become a good use cases for decentralized for distributive computing?
So I want to make sure I understand the question. So if you're in rural regions, how does that affect access to compute? Is that sort of, does that make sense?
No. It's more like in the case where I have like a lab that can host about 45 computers, and in this case, then and then of course there are learning that are continuous, or call centers and so forth, where now we're looking at probably a case for partnership. How do like in your own case, is there like a use case where we can have something similar working across together, and I'm not really like we're basically trying to find another value add-on to it, because we are looking at this.
Absolutely, absolutely, and in fact, let's put it this way. I want to speak as generally as possible because I don't want to limit any potential ideas that you may have. In fact, I'm even more looking forward to our chat on Wednesday. At the end of the day, this is a distributed computing platform that handles a certain type of workload, but it measures it. And then if it measures it, you can create any type of business model you want from those principles. So I'll share what we're doing in Canada so far. We've created so here's one model, the single tenant, self-consuming private compute network. So we're in about a dozen hospitals now in Canada, and each hospital is running its own private compute network in order to power optimization for their surgical block schedules. And again, the use case doesn't really matter here. What's important is that the entity has the use case, and it has its own computers that it's leveraging internally behind the firewall, so that it doesn't need to, not a single byte of data needs to leave the building, and they're not stuck with a cloud bill. So that's one use case, single tenant, self-consuming, repurposing existing infrastructure to get into the AI game without losing control of data and without losing control of the costs due to the commercial cloud. That's one model. A second model is if you had 10 hospitals, and right now we've done this with 3, and not all just in Canada, there's one in Brazil, where they each have their private compute networks and they each have their data sets. But as long as they're given, they trust each other, they can create a virtual bridge between their compute networks, and I can send a job to all 3 hospitals at the same time that analyze each data set, and only the results get sent back to me, none of the raw data. So this opens up, and this is called federated computing. So this opens up a really, really cool use case where you can have dozens or hundreds of campuses, schools, high schools, colleges, universities, whatever, who can either work independently or even pool virtually across regions. And using the compute credits, you can make sure that no one campus is using more than the other, because if it runs out of credits because they're greedy, or not greedy, but they just burn through their credits faster because they did more compute, then those credits end up in the hands of the other universities that can then they get their turn to, right? So it's this measurement is what allows fair allocation of computing resources within communities, whether they're closed ecosystems or open. And then okay, so that's people sort of sharing amongst each other. And then the obvious use case that folks are interested in is you can set up a computing cluster on your infrastructure. You can consume it yourself with your own use cases, but if you're not using it all the time, you can also sell it externally to some other consumer. So PwC, I'm just making up an example here. PwC definitely spends a lot on data science workloads in the cloud and whatnot as it's doing stuff for its customers. And PwC has a presence in Nairobi. Imagine if they were approached, or any other bank or any other entity, and they were approached and said, hey, why don't you take part in this sustainability, compute economics, local effort? What you're getting is 4 to 10 times cheaper compute compared to the hyperscalers. And that money then ends up in the hands of people who are providing infrastructure locally, schools, hospitals, whatever. And then that money can be used to refresh the hardware or advance, more objectives or what have you. So, and I'm just scratching the surface here, but what can you do if you have the ability to create arbitrary compute clusters with an accounting system where you can share or sell or buy? It's quite a bit. Sorry about that. David, back to you.
Yes, no, thank you, Dan. Sorry. We're right up on time, and I know we have one more question. I want to put up the slide for how to apply for the project, so that, or rather, to be part of this pilot. While Dan, you can go ahead and answer the remaining questions. So those who have time can stay on and engage. We're really excited to be here. I think Dan will have also a few more minutes before he has to transition. Caroline, is there something else that I need to?
Yes, I think we're running up until 6:30, so we're good. So we gave Dan 1 hour 30 minutes. Yes, so we do have some extra 30 minutes.
Oh, great! Excellent. Yeah. Then we have more than enough time.
Yeah.
I'll make sure then that Dan, you can continue.
And then... Well, it's probably a good idea now to bring up that page though. Let's activate that call to action now while people are still engaged. And there's nothing wrong with ending early either, so I'm okay with whatever people want to do. But basically, if anyone here has a distributable use case and wants to kick the tires on this and see if it's obviously delivers cheaper compute and all that good stuff, but more importantly, if the vision is attractive, where we can sort of as a community bootstrap a compute economy, please sign up, tell us about your use case and about your interests, and we'll get back to you, and let's do something cool. And of course, we're trying to do like 5 pilots, 5 use cases, of which there's like room for 3 more in the next month and a half. So maybe we won't select that one first, but we want a giant pipeline. We want as many as we can, because we're going to justify a follow-on mega expansion to do this big time. So please sign up.
Great. No, thank you, Dan. So we have then one other question from, I'm going to get this correct. Yes. Oluwa Funmilayo. You have the mic.
Hi everyone. Thank you for the presentation. I have a number of questions actually. I think part of it have been answered, but I'm just still going to ask so that I get more clarity. So are there data protection policies around the technology, as people would be sharing from their personal laptops? So are there data protection policies? And then I know you said the good stuff about the technology, but I also want to know if there's any major downsides that the people should know before subscribing or before joining the network. And then the payment to the users, say I want to use my personal computer for this, where does that payment come from? Does it come from people who have subscribed to the service? Or because I know, so this service is basically taken from like a major cloud, distilling it down so that different people can use their personal network and do computing over time. So basically, I just want to know how that payment system works. This is for my curiosity. And lastly, does the technology work for private networks too? Like if say, for instance, universities have their own network in-house and it's usually hosted on the VPN, and and they want to subscribe to a service like this where they can still use distributed computing instead of investing so much in GPUs. Would this service work in such a case, in such a scenario? Those are my questions. Thank you.
Thank you for those excellent questions. I'll try and hit them all here. So there's 3. I'm sorry, I'll put my video back on. Okay, so the first question is data security and everything else. And I want to make sure I understand, because cybersecurity and data privacy, that's a two-sided question. You want to protect the computer from the code, and you want to protect the code from the computer. And so not knowing which one you're referring to, I'll just answer a little bit of both. So the first one, if you are running a worker on your computer, is your computer safe from potentially malicious code? And the answer is we have a 99.999% confidence that your computer is virtually completely safe. And why? It's because, and now we go technical for 2 seconds, the compute engine in the software that's doing the computing is based on Google's V8 JavaScript and WebAssembly engine and Google Dawn's Web GPU implementation. So this is what allows for arbitrary and very, 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 very tight, narrow, secure compute environments on your computer. The primitives to access your local hard drives data or make network calls don't even exist in the secure sandboxes or evaluators, we call them, that are running code that's coming in. So if you are surfing the internet with Chrome, Safari, or whatever nowadays, you're just like surfing, what you're doing is you're loading code from who knows where onto your computer and computing, consuming it, and then moving on to something else. And that's only made possible because of these engines that are designed to securely execute untrusted code. That's what we've built this platform on, and so it provides pretty robust, very robust. In fact, the same security robustness as Google, because it's built on the same secure infrastructure. So that's one side. I hope that satisfies everyone from I mean, as quick as I can do in 2 minutes and less. We have 70 pages of security documentation architecture if people want to dive really in. So that's protecting the computers from the code. The other side of the question is protecting the code from the computers. So if you are deploying very proprietary algorithms and very sensitive data, and you're distributing it on computers that could be all over the world, well, what are the chances that someone somewhere that you don't know on the public network can reverse engineer and exfiltrate your algorithm and or data from the workload that they're working on? And the answer is that it totally is possible. You can trigger a RAM dump if you're sophisticated enough, and then forensically, sort of investigate what it is that was inside your that was running in your computer. And that's not just true for DCP, that's true for every computing system on the planet, including AWS. And the way AWS has solved this problem is to just put retina scanners and big locks and big steel doors on the entrance of their facilities, and then they tell everyone, you can trust us. We won't look at your stuff. And so the business answer to this is, if you have super sensitive algorithms and data, don't run it on public computing networks, run it on private computing networks where you know the entities providing the compute, which is a partial answer to your third question, but I'm gonna pause that and I'll come back to that later. There is a technical answer too. So when data and algorithms are in transit or storage, or like they're at rest or in transit, they're encrypted. But when they're being computed on, they need to be decrypted in order to perform the operations. And that's where the vulnerability comes in if someone were to really, dig in. There is such a thing as homomorphic encryption, which allows for the processing of data while still encrypted. It's not usable for arbitrary any type of compute. I think actually for machine learning, it's well established. There is something called full homomorphic encryption, which is attempting to be usable to keep everything encrypted no matter what, but it adds almost 100 times compute overhead. And so now it's a business question. Do people want to wait 100 times longer and pay 100 times more to have the satisfaction that their payloads are executed securely on arbitrary public library computers? The answer is probably no. They'd rather just run those workloads on private networks where they know the providers of compute. So that's the two-sided question for data privacy and security and an overview. We're only scratching the surface. Their second question is, where's the money coming from? Or how do you get it, etc. So right now, and I was sort of talking about the settlement layer earlier, PayPal is the current built-in mechanism for making sure that money gets from someone who's buying compute to the person who's providing compute. But we're totally eager and excited to build in other payment mechanisms, local ones that are local to Africa. So if there's payment processors that are local in Kenya, we should put those on this platform so that it broadens the options to everyone. I don't know if that's exactly where you're going with that, but basically, yeah, people who are spending on AWS, so they can basically decide to spend on this, and that creates a flow of money that's local. If no one wants to spend money, well, then the system doesn't work because that's how economies work. Your third question was around what are the downsides of this technology? And I love that you asked that. And I sort of hinted at it a couple of times throughout the presentation that this type of platform is not usable for everything. Really not. There's a Venn diagram of use cases that make sense. They have to be distributable. Okay, a lot of people are talking about ChatGPT and DeepSeek, inferencing, and that's not a distributed computing workload. In fact, it's worse than a serial workload. It's basically one node running one instance, providing a response to a prompt every 5 minutes, and it has to maintain state that whole time for that one user that's using it. So it's a serial job and a serial node, and there's a lot of idle time between prompts. Why? Because the use case usually is you're writing code, for example, you say, hey, how do I write this thing? And it gives you an answer, and then you copy it, you write it, you test it, you play around, you bang it around, you wait, 5 minutes later, you say, oh, I got this error, and then you go back. So LLM inferencing is not a distributed computing use case. LLM tuning or deep learning is a fantastic distributed use case. But here's the weakness, the current weakness. It's going to go away in the next 12 to 18 months, maybe sooner, with this platform. And it's the clue to this was embedded in the fact that we're running on V8 and Web GPU as the GPU and CPU backend engines. They give us unbelievable security in a way that no other platform can provide. Like we're talking about arbitrary, any code can be executed on any machine. Okay, so perfect interoperability and near perfect security, same as Google, which is security is a showstopper in a distributed computing network with an economy. So we had to get that one, but the trade-off was that TensorFlow and PyTorch, which are the two most popular deep learning frameworks, as everyone can attest here, right now they use CUDA backends, and their CUDA backends only speak to NVIDIA chips. So now you see the problem. So right now, WebGPU runs WebGPU shader language. That's the GPU language for WebGPU, not CUDA. However, this is the fun part. While we cannot run CUDA codes on DCP right now, and that's the major Achilles heel for us right now. 3 weeks ago, a CUDA to WebGPU toolchain was just put into the world. It's probably in beta testing. It's probably got a lot of kinks. So it's probably not ready for prime time. But the point I want to make is that the whole world is advancing and closing the gap between CUDA workloads and web GPU capabilities. And so that's my number one caution to everyone to manage expectations is if you have distributed compute workloads, talk to us, except if they need CUDA. If they use CUDA, if they need CUDA, still talk to us because we want to have, we still want to have like a long list of everyone. And guess what? If everyone wants CUDA, well, then we're going to have to divert our research, our R&D efforts to build those tool chains ahead of schedule. But if there are some use cases that don't need CUDA, but use sklearn, NumPy, XGBoost, or what have you, some of those other libraries, we can do those today and build momentum towards the really exciting stuff on a follow-on motion. I hope that was transparent enough of an answer.
Yes, please. Thank you.
Oh.
The last question was about people on private networks. How can they connect to this technology?
Okay, so for that one, now's probably a good time to segue into like an applied demo. And I'll be real quick about it. So let's see here. I want to use a simple example from my. So fittingly, the use case that I showed at the very start of this that electromagnetics example, I'm going to show you the code and the API behind it because everyone just saw a fancy shiny web UI, which really doesn't show much about the technology, does it? So, and apologies for those who are less code oriented, but this is getting down to the nuts and bolts. So I, as a researcher who doesn't care about DevOps and YAML files and Kubernetes clusters and all this noise, I just want to write my loops and my code and my functions and get my answers. This is what it looks like to program for this platform. Here's the main. Oh, and apologies. This is a Node.js example. We have Python examples, and if you prefer to see a Python example, I'm happy to switch over to that too. We can handle almost every language except for R. Okay, so main entry point for the function, we require the DCP compute API. Here we also require a range object, which is basically, it's kind of like iter tools, if you're familiar with that. So basically this is an array of arrays and it's doing the combinatorics on it. So this is the input set. It's an array, and if you recognize this, these are all the numbers that were on the web page earlier when I did that live demo. And so these are all the characteristics of that tube coil system. So these are the parameters or the arguments that go into the function, the model where I'm running those force computations. So basically the input set is this iterable array. The work function is here I'm calling it model. It takes a parameter set singular. Notice the parameter sets here was plural as an input. And then here I've abstracted away there's like 8 pages of math here that I did behind this. I called it, it's just another package that I'm importing, call it physics. I'm computing the axial force and the radial force applied to the parameter set input, and I'm returning a result. And then finally, very simply, the job is to take the model function that I wrote and apply it to each of the parameter sets automatically in parallel. So think about a hyperparameter tuning example, right? Or a k-fold cross-validation, or wherever there's like, you have like a for loop that you want to unroll and do in parallel. This is a for loop that basically, it's like MapReduce in a sense. It's a remote map. The job requires these packages. In a Python example, you could require scikit-learn, NumPy, pandas, whatever. And here, this is the interesting private compute group. So Sheridan is actually, this is Sheridan College. If I delete this line of code my job will go to the global group. If I include this line of code, my job will only deploy into this private compute group. And notice this is an array, so I can have a whole bunch of, I can send it to 100 different private compute groups if I have the proper credentials. But this is how, from the user's point of view, I can say only run my job on computers in this private compute group at this university, campus, or hospital, or whatever. Then I can give the job a public name, optionally or not. I can wire up some events, like print the results whenever one appears. And most importantly, results equals job.execute. That's it. So input set, work function, job equals compute.for, private compute group, a name if you want, some arbitrary, some optional events, results equals job.execute. And this will automatically take that job, spread out the computations across as many compute nodes, screensavers, or Docker workers as you'd have on the other side. And that's it. You get your results back. What does this look like from a worker point of view? So if I was at one of these institutions, here I'm going to show you like the Docker worker real quick. So here's an example. So I don't know if you see my command here. I'm Docker run the DCP worker, the latest image. The payment address is where the compute credits are being deposited when as my worker is doing work. And then I'm leaving the public group. So that means that this worker, this Docker worker, will not join the public network, and it will join the Sheridan group. So all I have to do is press enter. Oops, I need to run Docker, obviously. Second, just have to initialize set up Docker Hub, Docker Hub, Docker Desktop. Okay, Docker's running. And so if I run that, and voila, this worker is now live. It took 2 seconds, and it's ready to accept tasks that are deployed into the Sheridan Compute Group. And so if you're at a university or an enterprise or anywhere, and you want your own private compute cluster, let us know. We'll create a compute group, and only you will be able to use it. And if you decide that you trust another campus, then you can exchange credentials, and you can use each other's compute. And the metering it restricts people from being able to hoard all the resources, because the compute credits will bounce back and forth as an enforcement of fairness mechanism. Basically, you can't consume more than you provide, thanks to the compute sharing capability.
Thank you for your response. I think I have some clarity on it. Thank you.
Perfect. Thank you so much. I think there was questions around, this was an anonymous attendee, around redeeming credits, and a question around how do you do this as a personal, as an individual? Can an individual participate? So that was what Aquila was asking. She dropped off. I don't know if you want to answer that quickly.
Yeah, absolutely. So if you're an individual and you want to join the public network and pull down workloads that other people are deploying, you can run any one of those things. You can run a Linux worker, a screensaver worker. We even have a browser worker. And so I'll show 2 ways real quick to do this. The first one doesn't even require installation of anything. So if you type dcp.cloud, probably already logged in, and I have a lot of accounts. Maybe I'll log out. I'll join a one with less. I think this one has fewer in it. Okay, so this is dcp.cloud. It's a very simple username, password, sign up flow where you can register. But once you register and you log in, perfect. This is what it looks like when you log in for the first time. You'll have one account, and it's boringly called default, and there'll be 0 credits in it because, hey, it's a fresh new account. So the first thing you can do is give it a cool name like Dan's awesome account or whatever you want. And there it is. And so notice here, you remember this, see this address? Okay, if you mouse over it. Remember earlier when I when I ran this Docker worker and I put in a payment address here, that payment address was would be from this. So this is the bank account address. So I could copy to clipboard and I could go back over to my well, now I have to quit this worker. Or maybe I won't do that. I'll show the browser worker first. If you go over here to the worker tab, you can see that, okay, maybe I'll set this something more reasonable, like 3. I can run workloads just by clicking on start. And so this is going to fetch workload and it's going to start working on it. And it's going to deposit compute credits into this account, which will appear here. The other way you can do this is, like I said, you can set up a Docker worker by running this command and pasting in your payment address. And another fun way is to go to distributive.network. So what I'll do is I'll just /workers. And here's a couple of options. So the Docker worker instructions all here. The standalone worker and the browser worker are ready. We just haven't updated the website yet. Forgive me. But the screensaver worker one is fun because all you need to do is download the screensaver application. And there's a little video here that shows how to set it up. Here are the instructions here. But basically, once you install it, it shows up as the DCP worker screensaver right next to 3D text and bubbles in your control panel. And then when you configure it in the settings, you can set the bank account, which is this here. So you'd paste in that bank account address. And now whenever your screensaver is active, it's connecting to either the public network or to private compute groups. And this is how you configure it in the compute groups page. And away you go. All these different workers will execute workloads and pay into whatever payment address you provide, which you manage at dcp.cloud.
Thank you. That's very, very good. And do you want to show us, paying out of, because somebody has a hey, how do you redeem credits to withdraw money? I think you had shown like a 2-second one. And then I think we'll finish there with just the types of workers that we're, or rather the types of use cases that we're looking to do as part of this pilot program.
Exactly. And so here I resharing screens, you can see that the worker fetched and now it's executing slices of workload from the public network. And as it's doing that, it's accumulating some credits. These are small tasks. So whatever the person paid to deploy them could be high, could be low, probably low. In fact, it's definitely low. What I'll do is I'm going to stop and I'm going to log out. And I'm going to go back into my other account where I've been earning for a longer period of time. So got a lot of accounts here. But what I can do is, let's say my Dan account with 11,000 credits, the little widget here on the right, there's buy, sell, transfer, and donate. So buy is very obvious. This is when you want to fill your account with credits if you want to deploy workloads. Sell is also very obvious. It's when you want to sell. So if I do Dan, and I say I want to sell, I don't know, 10,000 credits, it just pops up a modal. And I put in my PayPal account and I hit sell, and then cash will be transferred to my PayPal account. So buy and sell. Okay, so back to the, and so what we want to do is we want to, and now everyone understands probably closer to what's going on here. This is what we want to create in the Compute for Africa compute group. We want to create a local economy where people can transact computing power, deploy workloads as easy as possible with high security, et cetera, pay and get paid. Cheaper compute because it's recycled computers, and also people getting money staying local. So that's the vision. In terms of use case, okay, so where are we now? If you are a data scientist or a computational, you don't have to be necessarily AI. You can do image processing or whatever, or statistics, or really, like, if you are a practitioner of that uses compute for your art, we want to talk to you. If your algorithms are distributable, we want to talk to you. We want to take your use case and we want to run it on this, and we want to do it at scale, and we want to, as a community, build a compute economy and accelerate research and discovery. here's examples, and this is not an exhaustive list. Here's a couple examples by field of application of data parallel or embarrassingly parallel algorithms that are suitable for distribution. As a machine learning scientist, some of these should be quite familiar to everyone. So if you're doing any of this type of stuff, it should work. Notice the random forest and bagging algorithms, genetic algorithms, particle swarm optimization, Bayesian optimization, Monte Carlo, what have you. Simulations and sampling, Monte Carlo methods. This is used in financial risk, insurance companies and banks. This is all they do all day long, is these huge Monte Carlo simulations. In fact, they would be perfect customers for this platform in Africa to rain that money back down on local providers. Bootstrap aggregation, MCMC, ray tracing, agent-based modeling, physics-based simulation, etc. Graph network processing, computation, MapReduce. So my example of physics was a MapReduce application, and it was used in physics for electromagnetic propulsion. So for numerical integration. What else? And bioinformatics. So we do have some use cases where we're doing multi-omics, genomics processing, looking for biosignatures in genomics data sets, which is wild, right? So if anyone's in the healthcare industry and you're doing genomic sequence alignment, or you're looking for biosignatures for particular rare diseases or what have you, bioinformatics is a really good one for distributed computing. And that's it. So one last time, the call to action is, if you have a use case, please reach out to us and tell us about it. We want to know what it is, and we're going to rank these use cases by which ones can we do immediately and which ones do we want to do later. But we want to get back to everyone.
Perfect. Thank you, Dr. Dan. Caroline, over to you.
Thank you. Thank you so much, Dan. Amazing presentation. And thank you so much, guys, for joining. And thank you so much, David, for moderating the session. So we've shared a link for you guys to join, to just sign up if you have an active use case you want us to test with DCP, so feel free to do that. We've also shared an email address. If you have any questions directly directed to Dan or David, feel free to do that. And then the other thing I need to mention is you're going to be hosting more webinars in future around compute, because I feel like with the questions you're asking, we need to have more discussions around compute in Africa. So that should be it, guys. Thank you so much. Have a lovely evening.